Hi, everyone. Welcome to today's lecture, which is all about correlations. You may be asking yourself, is there a correlation between me drinking some coffee and recording these lectures? Well, all will be revealed once you understand more about correlations today. And really, on a more serious note, correlations are really the bedrock of our understanding of the world around us. And they can be really powerful tools when our understanding of relationships between variables map on correctly to how the world operates. But it can be really problematic when statistically it seems like two variables are related to one another, and that informs our understanding of the world. But in fact, there are some other driving factors which are contributing to that relationship, and that relationship can be explained by some other factor. And this is really the foundation of multiple linear regression analysis. So that's something we'll come to in future lectures, but I really want to emphasize that what we learn in correlations today has flow-on effects to our understanding of exploratory factor analysis, in addition to our understanding of multiple linear regression analyses. And it allows you to answer these sorts of questions in terms of the relationships between variables and how that can inform our understanding of how the world is operating and behaviors, but also the inherent limitations as well. And that's really what we're going to focus a lot of today with our understanding of this statistics. So before we get into that, a quick recap of what we did in last lecture. We talked a lot about getting to know your data and the importance of really understanding what are the distributions of your data, the ranges of the measures within your data, and getting a sense of outliers or things that could perhaps skew the distribution. What sort of distributions do you expect to see in your data? And I really can't oversell the importance of looking at descriptives because, for example, in a research example for a paper that I've done that was looking at timelines in dementia diagnoses, I was initially looking at this data set with fresh eyes. The documentation was sort of people had intense knowledge of the data set and it was scattered around, so it wasn't really a coherent documentation process that's within the data set. And so people told me, oh, there's these measures in the data set, but no one provided further information to me. So I had to sort of explore the data as I would with any data set, even if there was documentation present. And so I was looking at this measure, which was date of symptom onset. And I was looking at the distribution of dates across years, and I noticed that I looked across the years and the months and then the days, and I noticed that there was this massive spike in terms of the day of symptom onset and also in terms of month of symptom onset, where a lot of them were at the start of the distribution. So we had this floor effect, right? If you remember from last lecture, the floor effect is where the bulk of the data is in the bottom of the distribution, and the ceiling effect is where it's in the top. And so I asked myself, what's going on here? And very quickly I worked out, well, in fact, that's how the missingness was coded. So because the date variable required some date to be put in, if someone didn't know what the day was, but they knew the month and the year, it was the first of the month of the year. And if they didn't know the day and month, it was the first of the year. So if they said something like, oh, I think my memory symptoms may have started in 2021, then the date, and they didn't know what day or what month, which is natural in the course of dementia. It's sort of a gradual onset. Then the researcher or clinician would just put down the dates, first of the first of that year. And what's fascinating is that it exposed this whole area of research in regards to, well, is this missingness, which should be inherent in the features of the data for dementia diagnoses, because not everyone has a precise date as to when they can pinpoint when changes in memory occurred, because it's gradual over time. Why was this not being reported consistently? And were other researchers perhaps either not reporting the missingness or not looking at the distributions in their data? So really foundationally comes down to the distributions matter, and looking at how the data is distributed, but also are those distributions mapping onto what we would expect to see in the data is really, really important. So that all comes from getting to know your data. So really can't emphasize that enough. Hopefully that story drives home the point. And again, types of statistics that we use, that it varies as a function of the level of measurement. So we have the nominal, ordinal, our interval, and our ratio levels of measurement. Hopefully at this stage you have a really good conceptual understanding and grasp as to what those levels of measurement are, and understand also how they influence the type of statistics that we can use. So it's critical to really have a sense that in what situations can you use nominal, ordinal, and interval and ratio data, and that really underpins whether our statistics are parametric statistics or non-parametric statistics. And then we talked about the effect of skew on central tendency. I've got some great questions coming up, so we'll come back to that. And then we focus on principles of graphing. And really, some of the foundational principles here were ensuring that the message of your data is displayed through the graph, but also that it wasn't misrepresented. And what we meant by that was changing scales on axes, changing or distorting the shape of the distribution. So all of these factors can really change how data is presented. And it's important to be very ethical, not only in your research, but also in the presentation and discussion of your data. And much of the times, I think you could pick up any paper and you could see that when people talk in their conclusions of their study, they say, oh, there was a statistically significant effect, or there was these variables are related and it's statistically significant. Now, the question that needs to be asked is, okay, it's statistically significant. Is the difference clinically meaningful? And often at times what you'll find is that the statistical significance may be there, but the size of the effect is, say, 0.02 or 0.03. And what the numbers are really, they need to be interpreted in context of the scale. So in the UK Biobank data set, for example, which I provided an example of previously, as to the type of data that's available in the data set, there is a cognitive measure called numeric memory. And it goes on a scale of 0, 1, 2, 3, 4, 5, all the way up to, I think, 12. And it's how many digits people can remember in a string of digits. And sometimes people use this measure and then they do analyses and they say, oh, it's a statistically significant result and we see a difference between these groups or relationship here. And if you look at the result, it says a change of 0.05 or 0.03. And then the question is, well, what does that mean in the context of a scale where the difference between numbers is 1, right? So we have to consider really what the data means and how that's explained within figures. And then again, if you look at the figures, they'll showcase that difference as being quite large. But if you look at the scale, they're going up in increments of, say, 0.05 or whatever their effect is, where really that y-axis should reflect the scale of the measurement of 0 all the way to 12, and then that would really balance out that effect and make it very evident that it's a difference between clinical and practical significance is there, or statistical significance there. So those are the principles of graphing, and then we also went over univariate graphing techniques. So excellent. Hopefully all of that is clear. If not, head back to the lectures and do some extra reading as well to learn a bit more about it. Or you could do some of these questions with me. So if a survey question produces a floor effect, then where will the mean, median, and mode lie in relation to one another? So I sort of gave away what a floor effect was in my previous spiel, but the floor effect is where all the data is sort of condensed at the bottom of the scale, right? And so essentially what you have there is positive skew in the distribution. So we have, it looks like all the data is in the bottom of the scale there. And hopefully you're remembering the thought process we went through when thinking about the mean, median, and mode. So we talked about how the mean was really sensitive to outliers. And so once we've identified its positive skew, so the tail's on the right side, we know the mean's going to follow that tail. So the mean is going to be closer to that right side. And then that's going to be followed by the median, which is in the middle, and then the mode, right? So it's mean, median, mode. So that's where they'll all lie in relation to one another. Now let's ask ourselves the question of like sort of a practical application. And hopefully you're pausing in between each of these questions to have a think for yourself. So would the mean number of cars owned in Australia exceed the median. How would you work this out? What do you think? I'm going to have a sip of coffee and realize also I don't need to have a sip of coffee because you can pause your video. So that's probably redundant. Sorry. But where do they? Where would each of these sit? Would the mean number of cars owned in Australia exceed the median? How do we answer this? Well, we have to ask ourselves a series of logical questions. For example, if we were to take a sample of people in Canberra and see how many cars they would own, what would we expect to see? And could we even do this in a sample of Australia? What would the differences be between each of these samples? And so let's take Canberra initially. I think you could argue that it's a city where there's good infrastructure to cycle, and there, ride a scooter or skateboard to work or to school or whatnot. So people may not be as reliant on the use of a car. And typically, if it's a family, they may have 1 to 2 cars. Certainly, maybe no more than three. Less on average, I'd say if you were to sample most families, they'd have less than three. Feel free to um, challenge that justification, but I think it's in somewhat reasonable. The cost of living, there's the cost of cars, their insurance, and every year all registration. There's a whole bunch of costs. So the less number of cars you have, the less these costs are. So I think it would be reasonable to assert that most people in Canberra in a household, would have somewhere between 1 to 3 cars. And if I wanted to be more certain about this, I could look at, say, government statistics and see, has there been some of this data collected in the past, and then extrapolate this elsewhere. Well, what about in other areas like Sydney or Melbourne, where there's higher population density, less reliable transport? Would they be likely to have more cars, less cars? What's the public transport systems like there? Cost of living, all these sort of factors. But I think the analysis as a whole, if you go through that sort of logical exercise, would be that most certainly on average, you'd be expecting people to have less than 3 to 5 cars rather than more than 3 to 5 cars. And so what that would produce is a floor effect. And really that's what that question is trying to get to, is that you'd have this positive skew. You'd have most of the data here, so then you have this positive skew, so the tail's on the right side. And we know that the mean is going to be following that tail. And so would the mean number of cars owned in Australia exceed the median? Yes, because the mean is following the tail, and the median sits behind the mean on a positive skew, right? So that's that question. Would the mean score on an easy test exceed the median performance? Again, easy test, now we're going the opposite way. All the scores are really high, so we have this ceiling effect. So it's a negative skew that's produced, and in this negative skew, we have the mean that sits more to the tail here, so on the left side, followed by the median and the mode. And so now the question is, would the mean score on an easy test exceed the median? No, it would be less than the median. So hopefully working through those examples helps solidify your understanding of floor effects, ceiling effects, negative, positive skew, and where these measures of central tendency lie in relation to one another for each of these types of distributions. Excellent. So the focus or overview for today is we're going to talk about covariation, purposes of correlation, linear correlation, types of correlation, interpreting correlations, and assumptions and limitations. So a nice full structure to help you with your understanding of correlations and their applications and strengths and limitations. In saying that, we'll break there and then we'll get back stuck back into it once we return. So I'll see you in the next episode. I'll see you very soon.